Vielen Dank, meine Damen und Herren, guten Abend. Ich begrüße Sie ganz herzlich zu dem heutigen Vortrag. Und ich freue mich, dass so viele gekommen sind. Zuerst erlauben Sie mir bitte, mich kurz vorzustellen. Mein Name ist Khaldoun Abaza, ich komme aus Syrien und ich bin seit September in Deutschland als Flüchtling. Wie liebe Merle gesagt hat, das ist nicht mein erstes Mal hier in Deutschland. Ich war vorher in Deutschland. Also 1998 bin ich zum ersten Mal nach Deutschland gekommen, wo ich in Stuttgart als wissenschaftlicher Mitarbeiter tätig war. An der Uni Stuttgart im Institut für Nachrichtenübertragung. Danach bin ich nach Ilmenau gegangen, wo ich meine Doktorarbeit geschrieben habe im Bereich der mobilen Roboter. Das war in der Fakultät für Maschinenbau und im Fachgebiet für der technischen Mechanik. In 2007 habe ich Deutschland verlassen, zwar nach Dubai, wo, wie gesagt, als Konstruktionsmanager in einer Baufirma gearbeitet. Und in 2011 bin ich nach Syrien zurückgekehrt. Sie wissen alle, was wir in Syrien haben. Also habe ich eine Arbeit gefunden an der Uni von Damaskus, aber es ging nicht mehr. Es war zu gefährlich, um dort zu bleiben. Also habe ich entschieden, nochmal nach Deutschland zu kommen. Also geforscht habe ich in Stuttgart und in Ilmenau. Gelehrt habe ich in Ilmenau und in Damaskus. Ich bin kein Spezialist, um das zu vergleichen, aber ich habe was erlebt. Also die Forschung leider bei uns in Syrien ist fast unmöglich. Um Forscher zu sein, braucht man Finanzierung. Das ist fast unmöglich zu haben. Noch ein Unterschied: als Lehrer an der Uni in Ilmenau hatte ich maximal 30 bis 35 Studenten und Studentinnen pro Semester. In Damaskus die Zahl war zwischen 800 und 1200 pro Semester. Und dafür bekam ich umgerechnet ungefähr 300 € pro Jahr. Also der Unterschied ist sehr groß. Forschen in Syrien leider geht nicht, obwohl wir haben viele, die forschen wollen und können, aber das ist leider unmöglich. Nun, jetzt komme ich zu dem zweiten Teil des Vortrags und den werde ich auf Englisch halten. Also, Titel meines Vortrags ist, wie Sie sehen, Design by Nature. Und es geht um mobile Roboter, besonders um die Lokomotion der Roboter. Roboter ist nicht so schrecklich, also weit. Okay, fangen wir an. Ja, danke. Nature is the greatest designer. We can't compare ourselves to the nature. It can provide us with ideas and solutions to accomplish any kind of tasks we want to accomplish or to solve any kind of problem we are facing. So today we are going to talk about mobile robots, but especially about the locomotion, the movement of these robots, and especially about a special kind of locomotion. So what kinds of locomotion do robots have? Nowadays, you can find robots that can jump, fly, dig, walk, roll, swim and dive. But what's important for us today is they can crawl. Crawling, the locomotion, the worm-like or the snake-like locomotion. The so-called undulation, the undulatory locomotion, which means, in simple words, the location change based on internal deformations with the help of the interaction between the body of this robot and its surrounding environment. We are going to talk in details about this later. An example for that is the snake-like locomotion. As you can see, there are different kinds of snake-like locomotion, and the worm-like locomotion, which is also an undulatory locomotion, but it's a special case of it. It's called the peristaltic locomotion, which means moving by using successive waves that go along the body of the worm or the robot. And it also, an earthworm uses these special needles attached to the segments of the worm, the so-called spikes, just to prevent the worm from slipping backwards. Here you can see a video of an earthworm moving forward. As you can see there, you can notice the waves we were talking about that go along the body of the worm. The maximum speed of an earthworm is about 1 centimeter per second, and to do so, it needs about from 5 to 20 contraction waves per minute. The body of the earthworm consists of segments, and it controls these segments separately to create the waves I have mentioned. To do so, it can, for each segment, change two things. Either the diameter of the segment or the length of each segment. Increasing the diameter of the segment means the length of this segment is getting shorter, and the other way around. If it's decreasing the diameter or making it smaller, that means the length of the segment is getting longer. So as an engineer or a scientist, if I want to design anything, I have to follow the steps of the so-called engineering design process. If you look for this term, you will find a lot of models, but I find this one very good because it shows how designers or engineers can jump back and forth between some steps or even skip some of them entirely. So the first step is to identify the need or the problem I'm facing that has to be solved. After that, I have to do some research and see what others have already done in this field. Select a solution, the best possible one, according to my opinion and my what I have learned or whatever, and after that, start building a prototype. After that, I have to test and evaluate this prototype. And according to these results, I may redesign and go all over again. So I can go back and forth until I find my final product, and then I can publish my results. So let's start with the first step, identifying the problem or the need. Why do we need earthworm or worm-like robots? It's simply because there are some areas or terrains inaccessible for us or other types of robots. For example, I can use these robots as inspection systems for technical diagnostics, like, for example, pipelines. I can use them in surgery. I can't insert a robot with legs or tires inside of a body. I need a worm-like robot to do the surgery. And other applications, maybe we can use them as rescue systems. So in this case, or for example, after an earthquake, I can send such a robot to look for survivors and then rescue them. So that was identifying the problem. As an engineer or as a student, I have to study this mathematically. So here you can see the earthworm, the body of the earthworm consists of segments, and here is the mathematical model matching this body. Here, it's for a lot of people is not the non-fun part because it contains equations, but as an engineer, it's a must. You have to do it. The movement of this model is defined by the distance change between the bodies. Here, the body consists of 3 bodies, and the length or the distance between each 2 bodies defines the movement. The change of L1 and L2 means I'm creating some kind of movement according to the so-called gate, the gate of movement, which is controlling this model. This is the actual prototype I have built. As you can see, the 3 bodies. By the way, these are actual slides from my doctoral thesis defense, so it's in German. Anyway, the 3 bodies of the prototype, the one in the middle is a dummy, passive one, just to complete the model. The other 2 are step motors that can go or travel along a threaded road connecting all 3 bodies, as you can see here, this road. So each step motor can go in both directions or can travel along this threaded road in both directions. And according to which step motor I'm moving, the sequence of it, I'm controlling, that's the idea about controlling such a robot. Here's a video about, you can see here this prototype moving. We can talk about that in details if you have questions later. Here you can see the first step. You can see that both the first and the middle body are moving forward. The last one isn't moving. And the second step, the other way around. The first body has stopped and the other two are moving. So the first step, we can say that the first or the last body is pushing the other two bodies. The second step, the first body is pulling these, the other two, the middle body and the last one. How, well, one remark here. Yeah, as you can see, in each step, both step motors are traveling along the road. Although the last body wasn't moving, that's because each body of them is equipped with a special spike structure to create the friction force I need to preventing the robot from slipping backwards. So it creates a non-symmetrical friction forces. That means the friction force for moving forwards is smaller than the one for moving backwards. And that's how it doesn't slip backwards. And this is a mathematical description of these friction forces. Another question I had, what about going uphill? How can I increase the angle alpha here? I want to maximize it. The idea, well, this is again not very beautiful, but you know, I had pleasure doing that. It was really interesting for me, and this is what is beautiful about mathematics. My idea was, well, to increase the angle, I have to add more bodies to the prototype, which costs a lot of money. Mathematics, that doesn't cost anything, and I can do it mathematically. So here you can see M means the number of the bodies I'm adding. At the end, the result I'm getting, it's all about the friction force. So my result was, don't concentrate on adding bodies or segments to the prototype, just concentrate on creating a bigger friction force. And like this, I can increase the angle alpha. This is the second prototype I have done. Now, before talking about this prototype, I have a question for you. What do a salamander, a cockroach, and an earthworm have in common? Well, nothing at all. They don't have anything in common. But this prototype is a combination of these three creatures. And this is what's beautiful about engineering. I can combine a lot of ideas or rules of the nature and create something else that normally doesn't exist. So it's a micro robot, small, 4.5 centimeter long, including the tail, that means it's small as a cockroach, and it has legs and tail like a salamander, although the salamander has 4 legs, but for my micro robots, I needed only 2 legs and a tail to create the 3 contacting or supporting points needed for the stability of this micro robot. And the tail is very important because it helps this robot in terms of stability and ability of maneuvering. Well, I have talked about the cockroach and the salamander. Where's the earthworm here? It's simply the principle of movement here, which we were talking about, the undulation, which in simple words is the deformation of the body. The body here, the body is the so-called piezo actuator. Actuators are devices to convert the electrical applied energy to a mechanical one. So by applying an energy to this actuator, it will vibrate, a very fast vibration. The 2 legs are passive, but because they are attached to this body, they will also vibrate. And according to their form, the end of each leg, let's call it the feet, will create a circle-like movement, one of these shapes, according to the frequency I'm giving or I'm using. How can I control such a robot? I can only apply it with energy, and it will do its vibration. So it can only go in one direction. But there is a possibility for controlling or steering this robot. And this is a mathematical description of the idea. If the 2 legs are shaped exactly the same, they would do always the same kind of movement. But if they have a slightly different shape or form, that means the resonance for each leg is different. So I'm displacing the resonance for the 2 legs, and if I use the frequency in the middle, here the value of the amplitudes for both legs is the same. So they will do the exact same movement, and the robot will go forward or backwards according to the frequency. If I want to steer it to the left or to the right, I will simply change the frequency. If I use a smaller frequency, here, for example here, the amplitude of the right leg is 0, but maximum for the left one. So the left leg is doing this movement, the right one isn't, and the robot will go to the right. And the other way around, if I want to control it or steer it to the other direction. That was the idea. So the idea was to create a micro robot which is fast, you will see shortly, and it can be controlled. These are simulation results supporting the theory done by ANSYS. And here I have to do it manually. This is an animation. As you can see, the body is vibrating, and the leg, because it's attached to it, doing its own vibration and creating the circle-like movement to create this movement. That's the animation. What about the actual movement? That's it. So it's pretty fast. Micro robot. By the way, that's me. But we can't see the actual movement of the legs in here. So I had to use a high-speed camera. Here you can see. Is it good? Can you see the movement of the legs? Yeah. This is done with 6,000 of pictures per second. So it's very fast. If you hold the micro robot, you will hear the vibration. You can feel it, but you can't see it. Yeah, that was my two prototypes. Short description of both of them. Now, in general, as I said, nature is the greatest designer, and we are always learning from it. But what robots actually can do nowadays? I have found this video on the internet, hoping you will enjoy it. What they can do, they are sometimes not so sensitive. Sometimes they don't have time. They have to do their thing very fast. They can have fun also. This is a proof that alcohol isn't the best solution, and it's dangerous sometimes. I don't know what that is, but apparently robots also need their freedom. And they can be violent. Entering politely, they love ketchup very much. Some of them are creepy, like some of us. Even the Japanese aren't perfect. And this is Cristiano Ronaldo against Manuel Neuer. So the actual, maybe the right question about this, what can't do, not can do. Nature, as I said, can provide us with ideas and be a good inspiration for us to solve any kind of problem we might face. All we have to do is to observe, study, and learn. But we have always to be careful, because tornadoes, volcanoes, and earthquakes are also part of the nature. Thank you very much.